Hi, Professor. Let me share
Yeah.
my screen.
Okay.
Can you see my screen, Professor?
Yeah, I can see your screen. Yeah, so the ideally your time should be like 20 minutes, okay? But no more than 25 minutes. Okay.
Sure, sir. So, well, I will be starting about the project, overview. So, well, our project name is diabetic retinopathy detection. So, I'll just go with the next slide. Could you please move to the next one? So,
Yes.
well, I would like to give you a brief about what is actually the disease is about. So, well, diabetic retinopathy is a complication of diabetics that affects the retina. That means the light sensitive layer of which is always in the backside of the eye. When it occurs only in high blood sugar damages, tiny blood vessels in the retina will be formed, and there will be some swelling, and the blood gets blocked in the retina and in the eye, and vessels leak, and in the advanced stages and all, there's some abnormal new blood vessels will be growing up. So, well, we have given few classes to this. For each and every classes we have given a name. For class one, it's a mild attack. Mild stage, or else for the class two, a moderate stage, or for the class three, severe stage, and for the class four, advanced stage. So, so we have been divided the damage in this way. So, well, I will be moving to the next slide. The whole problem is this. So we would like to detect this kind of disease with some AI models now. So for this, we have before that we have gone some LSTM model. Well, we have made some our own research and all. Well, it didn't go on well. That LSTM algorithm didn't work for this image recognition kind of things. Only we have on our research we have got to know it works only some text recognition and speech recognition kind of a thing. So, well, we have moved to different algorithms. So we have tried to build the CNN model. So we have trained our images and all. Based on giving some classes, and I started evaluating the model and building. Trying to get all the metrics and all. And we have tried to build a proper user AI where a non-techie guy also can able to upload their data and see what all the results will be happening. While coming to the next slide, um, so the adjacent, as I've already told you that the main problem was to detect it with the more AM proper AI model, and for the data set and all, we have taken data. Taken the data from the third party source, which is which is properly licensed and all. We haven't used any fake data and all. So, and while coming to the approach, as we have said, we have used different algorithms, but the efficient algorithm was which have worked properly was for us is ResNet 50, and the results and all will be shown in the end of this, and even for the UI demonstration will be given in the end of this presentation and all. So, while conclusion and all, everything will be explained by my teammate in the end of this presentation. Next slide will be presenting by my teammate. So next slide.
Yeah, this data source description, we used the IDRE data set, the Indian diabetic retinopath image data set, which is a publicly available expert annotated benchmark, which contains 500 high resolution founders images labeled across 5 severity of classes, like from 0 to 4. We can run with the no DR and proliferative DR. Having a ophthalmologist annotated label gave us a reliable ground truth to train against. Uh, with the class definitions of label, it was like 5 classes will be from the 0 to 4. And for the next slide, please. And data exploration. Before modeling, we did a throughout exploration and found 3 key challenges. first, a significant class imbalanced. The mild category had fewer samples. Secondly, visual similarity between adjacent severe levels, especially moderate and severe. The differences in lesions are quite subtle. And third, the image variable in terms of brightness, contrast, and noise. These challenges together make this a generous hard classification problems. Next slide, please. And data pre-processing. To address these challenges, we applied a full pre-processing pipeline. All images were resized to 224 224 for a uniform CNN input. These pixel values were normalized using image net statistic to stabilize training. We also applied augmentations, rotations, and horizontal flipping to boost diversity and reduce overfitting by this. And finally, labels were extracted from CSV files and encoded numerically. Oh, and the next one of our teammate gonna be continued for the next slide.
Yes, thanks. Hi, Professor. Let me go through from the modeling and methodology. So coming on this, like for our modeling approach, so we see that the leverage transform learning. So as a technique, like we start with our model pre-trained on a large data set. Like we have used the ImageNet and the fine tune in our medical images, which for that. And we also evaluated the two architectures, that is like one is the efficient net and the second one is the RISC-Net 50. So we use like a cross entropy loss. So as our loss function and Adam optimizer. So like which is we are the standardized choice for the multiple classifications. So let me go through the second one. So here the training process, which is very important in our thing. So we trained across the multiple approaches, like monitoring both training and the test accuracy. So detect overfitting early. So the dropout layers where we added as a regulation technique is like we saved the best performing checkpoint. So based on the test accuracy, when we have that done, and we observe the consistent improvement in accuracy as a training progressed also. Let me go through the other slide. So the result and evaluation. So where we are here on that. So the test accuracy is 54 to 58%. So overall test accuracy landed in 54 to 58% range. And we also evaluated the model using like a precision, the recall, and the F1 score, which give the more nuanced picture than accuracy alone. So especially like with imbalanced classes. So this performance, while not state of the art, is in line with the expectations of a like small data set with fine grained class justifications. So let me go through the confusion matrix also, which I want to briefly explain on this. So the confusion matrix like helped us like more understanding where the model was falling in the starting stage, the 54 to 58. So as expected, like like a classification, like misclassification, we done this like clustered between the adjustment severity classes. So for example, let me say like the moderate being confused with the server when we done that. So like this thought like tell us about the modeling like is learning and the general skill of diseases. But when we done with the more like the struggles with the borderline cases, like we saw that, and also which is consistent with the how even clinicians sometimes disagree on staging. Let me go through the model comparison also. So in the model comparison, so we see that intensively which comparing the our custom in the CNN, which like read around 94% accuracy against the reset net at 92%, where we can see this here. And CNN edged out slightly. So however, we selected the RISC-Net 50 as our final model, which given the strong generalized and robustness from the transform learning. So the raw accuracy gap was very small, but resetness architecture offers better feature and extraction of unseen data. So from here, my teammate will pass on.
Hi, Professor. Professor, can you hear me?
Yeah, I can hear you. Yeah, please go on.
So the key insights are four main takeaways from the modeling phase. The modeling performed well on clear, distinct cases. No DR or proliferative DR. There are early stage detections. Particularly mild was the hardest, but uh, misclassification was most common between visually similar adjective classes, and class imbalance consistently hurt performance and underrepresented categories. Like the UI implementation to take the model usable, we built a front-end interface where a user can upload a rental image and get a predictive severity class back in real time. The goal was to take the model accessible to non-technical stakeholders. A clinical should have not be to run Python script to use the tool.
So these are the screenshots that show the UI in action. You can see the uploaded fundus images on one side and the model's predicted class label on the other. The interface is clean and straightforward, designed for practical use, not just demonstration. And to wrap up, we successfully built and deployed a deep learning pipeline for diabetic retinopathy classification. Despite the inherent difficulty of the dataset, class imbalance, visual similarity between stages, and limited size, we achieved meaningful results and validated the validity of automated screening as a concept. There's there's a lot of room to grow on the data side. We'd look to use a larger, more balanced data set and explore oversampling techniques like SMOT. On the modeling side, we would experiment with more advanced architects and assemble methods. Clinically, the next step would be validation with real ophthalmologist feedback and potentially integrating the tool into a EHR system for the real world use. So, thank you.
So from our side, we will also be showing you the execution and what are all the things. I mean, what are all the based on the feedback and all, we will be showing what all the work is being done just in a minute. So my teammate will be showing you the code and all, and also the output of the code.
Mhm.
So while coming to the IPYNB file, could you please open the IPYNB file, Jupyter file? So this is the UI. The overall UI was being given in this way. I have already told you that even a non-techie guy is able to upload his details and all, and he can be see all his. I mean, what are all the probabilities and all will be shown over here. Even I would like to show you different images, uploading some different images and all. Even for this kind of a thing, when we have taken the data, when there was they were already given a data set, I mean, an Excel sheet of where it has everything about these images and all. So what else we have done is we have taken, though it has given us a training and testing data set on all, but we have taken the training data set and we have just split into two parts. One is for training and one's for testing. So, but still, at that time, I mean, we were trying to train the model in a way to gather where, I mean, we are trying to put all the information, trying to gather all the parameters in the code, to just how can I say, to to train the model where the model can gather all the information about the images and all. So we have tried first and with the CNN model. Well, it has, I mean, we have tried with the 25 epochs. It has taken at least 7 hours of a time to run the to run all these emojis and all. Although it has given a best accuracy, but the test accuracy was failing. But we have gone to ResNet 50 and in the finally when we have tried and also testing with the images and all, where I have compared with the data and all. So we found that the results were getting accurately based on the data which they have been given. We have compared each and everything. So we have got to know that we have finalized with the ResNet 50, and that's the one we are trying to show you now.
Okay, great.
Any questions, Professor?
No other question. Yeah, I think yeah, we can move on to the team number 2. So in team number 2, so the title is AI versus human text classification. So if team 2 is here and you are ready to go, you can just share your screen.
Yes, Professor.
Okay. Yeah, I can see your screen.
Hi, Professor. Can you see my screen?
Yeah, sure. You can start.
Okay, Tanisha, you can go ahead.
Okay. Good afternoon, Professor. Good afternoon, everyone. So my name is Tanusha. I'll be presenting.
Yeah,
our
can you like
topic.
make that into full screen? Yeah, switch to the full screen. Okay, yeah, that's better.
Okay. So our project title is AI versus human text classification. So we are from team 2. I'll be starting off with a presentation, and then my team members will continue once I'm done. So I'll start off with the problem statement and the motivation behind our project. So basically, with tools like ChatGPT and AI tools becoming like very common these days, it's getting harder to tell whether a piece of text is written by a human or if it's generated by AI. So, so the problem is that AI can write in a way that looks very natural. So it's not easy to detect anymore. So because of that, it's like becoming a challenge to make sure the content that we see online is like actually authentic or original. So that would be the problem statement for us. And the motivation behind this project for us to, complete it is because of the issues that we are facing in real life. So basically in academics, for example, student might be, using AI to write their assignments or whatever tests or whatever it is. So AI can generate like fake information, or it might sound, very convincing, but it can lead to, misleading information. So in areas like journalism or publishing, this can become a real problem. So whatever we read online is not 100%, accurate. So that is our problem statement and motivation. So moving on to the goal of our project or the project objective. So we plan to build a system that can figure out whether a text is written by a human or if it's generated by AI. We're using machine learning models to do this. So basically, we'll evaluate how they will perform using few of the metrics like accuracy, precision, or the FN score. So we will also be comparing how models perform. Like we basically selected 4 different models: logistic regression, Navis Bayes, SVM, and the other one, Distilbert. So we have compared how all of these models perform when it comes to, like classifying whether a text is AI or human written. So the agenda for our presentation or the coming topics is that we'll be explaining you about data collection, how we collected the data, what we did with the data, basically, like the pre-processing or, the the initial phase, and then the methodologies that we used, and the results we were able to produce, and then the conclusion. Okay, so I think next, Ravi Teja, do you want to continue?
I think Arvind can continue.
Hi, Professor. Good afternoon. My name is Arvind, and I'm gonna continue from now. So I'm gonna continue from the data source and description. Okay, so the data used in this project was obtained from Kaggle and contains a large collection of text samples. These are written in both human and AI systems. So it contains of two main columns, like the text itself and a label indicates whether the text is human written or AI generated. After cleaning the data sets containing approximately 487,000 samples, providing a strong foundation for training the test and evaluating our models. The data set is well balanced, ensuring fair learning across both the classes. And well, coming to data exploration, during the exploratory data analysis, we examine the distribution of target variables and found both the classes are like fairly balanced as compared to AI, and the human written are fairly balanced. So we also analyzed the text length and observed the dataset contains a wide range of text sizes according to like AI generated. So making it suitable for text classification tasks. One key observation is that AI generated texts tend to be formal way, uh, more formal and consistent, while human written text shown more variable and creative and occasional errors were like found in human written. Can you go to the next slide? Okay, so and while data processing, so to prepare the data for modeling, we perform like several processing steps. This include removing missing values and the duplicate entries to avoid the bias. And also we converted all the text to lowercase and removed a lot of things like unnecessary elements and URLs, punctuations, and extra spaces. So this avoids the text to be help reduce noise and improve the quality of input data, allowing models to learn more effectively. And the next slide.
Okay, I'm gonna continue from there.
Okay.
Okay, Professor, this is Ravi Teja. I'm going to explain the models and methodology. So actually, we use like these machine learning models for the test classification, such as logical regression, Navy Bayes, and linear support vector machine and the Distilbert. Going forward, so I can explain like why these models are chosen for the whole project. Going to the logical regression, it is set to like strong baseline performance on the text data, which is like easy to interpret and works well with the TF-IDF, which is the main thing that we worked on. And going to the Navy Bayes, this is chosen for like efficiency and strong performance in exactly the text classifications. And this is very fast and performs well with the small data sets and works well with the data like word frequency features. And going to the linear SVM, it's the same thing we use for the strong performance, but with high dimensional data for the sparse features. This especially works well for the high dimensional data. And going to distill, but as you mentioned, we like classify the data into like 5,000 and 500 samples so that we can test it in various ways. And these are the evaluation metrics used for the accuracy, precision, recall, and F1 score, which are going to calculate the whole model's data. These are the results and models evaluation. The best performing model for is linear SVM, which has like a highest accuracy, and the same for the precision, recall, and F1 score. We also use the Distilbert, which is a transfer based model. It also has some good results regarding the metrics that we use for the whole project. And coming to the naive Bayes, it is kind of quite moderate. It is fast, but it is slightly less accurate than the linear models. I'm going to explain about the like best model selection for the linear SVM. It is consistently at achieving highest scores for all the evaluation metrics. The model heavily relied on important discriminative works and patterns. Coming to the TF-IDF, it is differentiating like which text is human and which text is written by the AI. So this will raise a clear decision boundary to classify both the texts by using these traditional models. The conclusion. So we successfully like distinguish what text is written by AI and what text is written by like which is AI generated. All the four models were performed well, but regarding that, between from them, the linear SVM was the best model for our project. Going forward, Sairam will explain.
Hi, Professor. My name is Sairam. I'm going to explain about the limitations and the future work of our project. Mainly, the limitations we face, like the first thing when we are doing like the TF-IDF based models, we could not capture the deep conceptual meaning, which can limit the performance on the complex text. In the second, like the AI generated, advanced AI generated text, which is resemble the human writing, like the which will make more difficult to uh, classify whether it is like the AI text or the human text. Additionally, there will be a overlap while we take an AI text, and if we want to edit the AI text into a human text, it will make us like more difficulty to find out whether it is like written by the AI or like it is like a human text. Our database also may affect the well model performance on the real world data. In the future work, like we want to improve this system, like more like we want to train with the more data set, and we want to use like the more models, so we can capture a large data and we can train more data sets with the model. Next slide. So while training with the more models, we can improve the efficiency and the accuracy of the machine. So we can know whether the text is like the AI or human text comparison. In the next one, we have the results and the output for the our project. We created a simple HTML classification model where we can paste any data text from our data set. So we can, if we press the classify text, it will show like which model is giving like the what's the prediction, like whether it is the like human or the AI. I I can show you the when I will share my screen and I will show you the output. Professor, can you see my screen?
Yeah, I can see your screen.
Yeah, if we go to like any of our data set and if we copy and paste like any text in our thing, and it will give like whether it is like the human written. As we see here, logistic regression, it is like predicted as this is like the human written text. All the models are given like the and if we take like some other data, this is like the AI generated text. Mostly when it is like grammatically perfect and all, it is giving like the AI generated text. And we have separated the data set using like the for the AI we have given 1, and for the human text we have given 0. So it will be easy for the system to decide predict whether it is like the AI generated text or the human generated text. As we conclude, mostly our best model is like the linear SVM, and the next second model is the logistic regression, Distilbert, and the naive Bayes. Also, as you told, like the in the TF-IDF logistic regression, you told us to perform the 5,000, 10,000, and the 500 count with the less data set and the more data set at one time. So whether we know we have done that one too, and we got the accuracy good. Mostly we in our thing we can show you the outputs, like we got mostly like 99% accuracy in most of the models, and in the naive Bayes we got like 0.94% accuracy. So our SVM is the best model, and we want to conclude. Thank you for the opportunity, and thank you, bro.
Yeah, so I was wondering, like, like your system, right? So currently you're just showing, like, this is like you already prepared the data set, right? But how about, like, for example, if you just randomly open the ChatGPT and ask the AI generate to like a generator to generate some
Any
content.
text you want me to
Yeah.
do that,
Yeah,
I can
yeah,
do.
yeah. Can you show, like, if this is like yeah, because this is only based on our training set, right? So what uh, yeah, what is just randomly just generate. Yeah, you can copy and paste to check, well, if this is the
Yeah, it has given all this as like a AI generated text.
Okay, well, yeah, that's great.
If we
Okay.
want to type, we can type any of that also. If we like, if you want to type, it will give like the AI. If you type anything also, it will predict.
Okay. Little different, right? So three are like classified as a human written, one is AI generated. So how about like the text? So for example, here, the text here, how many words? Is there any limitation on the words number?
What's number, we did not like any limitation based on the trained data set. Some of them are
Okay.
like more words and some of them are like less. If we just say like hello also, it will predict mostly like as AI and human mix, because AI can
Okay.
also generate the same word and human written also,
Okay.
it will be the same. So if it is like
Okay.
the more words based on the grammar and all, it will detect whether it is like the AI and all. If you train like more data set, the accuracy will be increased and more.
Okay. Yeah. Okay, great. Yeah. So no other questions, so we can move to the next team.
Thank
The
you,
team
Professor.
number 3 is also the same topic. Yeah, I think NLP topic is quite popular.
Hello, Professor. I'm going to share our project. My
Okay.
teammates are going to explain our project. Professor, can you see my
Yeah,
screen?
yeah, I can see your screen and my
Thank you.
big face. Yeah.
Yeah, my teammate will continue the presentation.
Okay, go ahead.
Hey, Emma, can you expand the screen, please? Yeah. Hello, Professor. Can you hear me?
Yeah, I can hear you. Go ahead.
Yeah, good afternoon, everyone. My name is Pawan, and on behalf of my teammates Hema, Shravani, and Mukesh, I am pleased to present our graduate capstone project title, AI versus human text classification, a machine learning model to distinguish between human and AI generated text. This project was completed under the guidance of Professor Leo for the graduate seminar program at Governor State University. Today, we will present our complete journey from problem identification to a fully deployable classification system. Moving to the agenda of our project, our agenda today covers 12 key areas. We'll begin with the problem statement and motivation, followed by our project objectives. Then we will discuss our data sources, exploration, and key observations. After that, we will cover pre-processing and feature engineering, our modeling methodology, and our results across baseline, deep learning, and optimized models. We will then present our robustness testing, discussion, and business insights, conclusion, and future work, followed by a live demonstration and some quick questions and answer sessions. And coming to the problem statement and motivation, the core question driving this project is how can we accurately distinguish between text written by humans and AI generated by text generated by AI systems like GPT-4 and Cloud. This question matters because the rapid growth of large language models has created significant challenges across multiple industries. In academia, institutions struggles with AI-assisted cheating and plagiarism. In human resources and recruitment, verifying the authenticity of candidate submissions has become increasingly difficult. Now, media and journalism organizations battle AI generated misinformation that can be spread rapidly across social platforms too. And government regulatory bodies need tools to support ethical and transparent AI use. The impact of our work is substantial. We have analyzed over 500,000 essays, achieved 98.64% final accuracy, and developed a real-time classification system accessible through a web interface. And now moving to the project objectives. Our primary objective was to build a machine learning model capable of classifying text as human written or AI generated with at least 94% accuracy. Our secondary objectives include extracting meaningful linguistic, statistical, and semantic features, comparing traditional machine learning approaches against deep learning, validating model robustness across different scenarios, and deploying a user-friendly web application. Our success metrics were clear. We aimed for accuracy of 94% or higher, which we exceeded at 98.64%. We also targeted precision, recall, and F1 score above 90%, of all which we achieved. Finally, we required robustness across out-of-domain text and typographical errors, which our model successfully demonstrated. Now, moving to the data sources and description, our data came from a publicly available Kaggle dataset titled AI versus Human Text, created by Shane Jeremy. That dataset contains over 487,235 essays after cleaning. Of these, 305,797 samples, representing 62.8%, were human written, while 181,438 samples, or 37.2%, were AI generated. The average text length was approximately 2,270 characters, which is about 393 words. The dataset has two main columns: text, which contains the raw essay content, and generated, which is a binary label where 0 indicates human written and 1 indicates AI generated text. Now I will hand over the presentation to my teammates.
Hello everyone. Professor, can you hear me?
Yeah, I can hear you.
Um,
Go ahead.
sure. So, coming to the data exploration and key observations, our exploratory data analysis revealed three main observations. Firstly, as shown in the class distribution chart here, the dataset was significantly imbalanced with 62.8% human written samples. Training on imbalanced data would bias the model toward predicting human text and also resulting in poor AI detection performance. So what we did was we addressed this by applying random undersampling to the majority class to achieve a balanced 1-to-1 ratio. Secondly, both human and AI text showed similar length distributions, with most essays mainly ranging from 1500 to 3000 characters. So this indicates that text length cannot alone be used to distinguish feature. And thirdly, our feature importance analysis revealed that linguistic features, including the sentence length variation and parts of speech frequencies, were the most important predictors, significantly outperforming like the pure statistical features. Hema, can you go back to next slide? Yeah, thank you. Coming to the data preprocessing and feature engineering, our preprocessing pipeline consisted of 6 main steps. Firstly, we removed the missing values. Secondly, we performed text cleaning, including lowercase conversion, URL removal, email removal, and encoding fixes. Thirdly, we removed both exact duplicates and near duplicates using min hash with a similarity threshold above 85%. Fourth, we filtered out text shorter than 20 characters. Fifthly, we balance the data set by undersampling the human class to achieve a 1-to-1 ratio. Finally, we split the data into training, validation, and test sets using a 70-15-15 split. For feature extraction, we generated three categories of features. The linguistic features included sentence length variation, vocabulary richness, part of speech frequencies, and also the passive voice detection, totaling of 16 dimensions in total. Statistical features included TF-IDF vectors, n-gram patterns, and perplexity scores, totaling 10,000 dimensions. And the semantic features used Glovewood embeddings with 300 dimensions. Can you go to the next slide? Yeah. Coming to the modeling methodology, we evaluated three categories of models. The baseline machine learning models included logistic regression, SVM, the support vector machine, and random forest. Our deep learning models included an LSTM with 128 units using Glove pre-trained embeddings. Our transformer model was a fine-tuned Distilbert. We chose logistic regression because it is interpretable. We chose SVM because it handles nonlinear boundaries well. And we chose random forest because it provides feature importance. For deep learning, we chose LSTM because it remembers context from previous words. We chose Distilbert because it is fast, lightweight, and the state of art for text classification. All training was conducted on Google Colab using Tesla T for GPU resources. For evaluation, we used standard metrics including accuracy, precision, recall, FN score, and AUC ROC. Accuracy is calculated as true positives plus true negatives divided by the total samples. Precision measures the proportion of positive identifications that were actually correct. Recall measures the proportion of actual positives that were correctly identified. The F1 score is the harmonic mean of precision and recall. Coming to the baseline model results. Here, our baseline model results showed that logistic regression achieved the highest performing among the traditional machine learning models with 79.32% accuracy, 69.53% precision, 80.97% recall, and an FN score of 0.748. SVM achieved 76.76% accuracy, and random forest achieved 76.82% accuracy. Our feature set comparison revealed an interesting finding, like the linguistic features alone achieved 80.50% accuracy, which was actually higher than the combined feature set. Statistical features alone performed poorly at only 49.88% accuracy, and semantic features alone achieved 51.02% accuracy. This suggests that Stylistic and syntactic patterns are the most reliable indicators for distinguishing human from the AI text. Coming to the deep learning results, our deep learning models significantly outperform the baselines. The LSTM model achieved 99.79% validation accuracy and 98.30% test accuracy with an F1 score of 0.978 on the test set. The transformer model, which is the fine-tuned Distelbert, it achieved 95.33% validation accuracy and 95.40% test accuracy with an F1 score of over 0.948. Both deep learning models far exceeded our baseline results and achieved the 94% target. We then optimized the transformer model using optimal hyperparameter tuning. The optimal configuration identified a learning rate of 2e-5, batch number of 16, 3 epochs, weight decay of 0.01, and 500 worm setups. And now I'll hand over the rest of the presentation to my teammate Mukesh. Thank you.
Yeah, thank you, Shravani. Am I audible to you, Professor?
Yeah, I can hear you. Yeah, please go on. Yeah, you can go ahead.
Mukesh, we cannot actually hear you. Are you presenting?
Am I audible now?
Yeah, you're audible.
Yeah.
Okay, thank you. Our final optimized transformer achieved 98.64% accuracy, exceeding our 94% target by over 4.6 percentage points. Precision was 98.10%, recall was 98.40%, F1 score for 98.23%, and AUC ROC was 0.997. The confusion matrix shows 41,528 true negatives, 140 false positives, 760 false negatives, and 25,897 true positives. The error rate was only 1.36% with 1,001 errors out of 68,337 test samples. Robustness testing. We conducted 3 robustness tests to validate our model's real-world performance. Firstly, out-of-domain testing on completely new text domains, including news articles, scientific abstracts, and creating writing, achieved 100% accuracy. The model correctly classified all 6 test samples across different domains. Secondly, adversarial testing with typographical errors showed that the model maintains 96.50% accuracy with 5% typos, 94% accuracy with 10% typos, and 88% accuracy with 20% typos. This model maintains over 94% accuracy even with 10% typographical errors, demonstrating the strong robustness to real-world input variations. Third, text length sensitivity analysis shows consistent performance across all the text lengths. Accuracy ranged from 94.69% for very short text under 50 words to 98.95% for text over 1000 words. Can you scroll this side? Okay. Discussion and business insights. Our keys of finding are 3. First, linguistic features are most predictive. Human writing exhibits greater stylistic variations in sentence length, vocabulary richness, and part of speech patterns compared to AI-generated text. Secondly, deep learning significantly outperforms traditional machine learning with LSTM and transformer achieving 98.30% and 98.64% accuracy respectively. Compared to logistic regressions at 79.32%, and thirdly, a model is robust, maintaining over 94% accuracy with 10% typos and performing well across all the text lengths. However, we acknowledge several limitations. Our model currently handles English-only text. It may require periodic retraining as new AI models emerges. It also struggles with short text under 50 words. The business implications are very significant. In education, the model can detect AI-assisted cheating in student submissions. In human resources, it can verify the authenticity of candidate resumes and cover letters. And in media, it can filter AI-generated misinformation before publication. And in legal context, it can authenticate document origin in legal proceedings. Conclusion and recommendations. In summary, we successfully achieved all our project goals. Our final module exceeded the 94% accuracy target, reaching 98.64%. We built a complete deployable system with a Streamlit web interface. And we validated model robustness, maintaining our 94% accuracy even with 10% typographical errors. Our recommendations are as follows. First, deploy the model as a web service for academic institutions. Second, schedule periodic retrainings quarterly to adapt to new AI modules. Third, integrate with existing platforms such as learning management systems and HR systems through API. And fourth, expand the multiple languages for global applicability. Future work. Looking ahead, we have identified several enhancements for future work. High priority includes periodic retraining for new large language modules such as GPT-5 and Claude 4. Medium priority includes multi-language support for Spanish, Chinese, and French, as well as mixed content detection for AI-edited human text. Lower priority, it includes real-time API development for live content moderation, SHAP and Lime integration for model interpretability. The key takeaways for our project are clear. We successfully achieved 98.64% accuracy, exceeding our 94% target. We built a complete deployable system with a web interface, and we validated model robustness across multiple real-world scenarios. My teammate Hema will be taking you to the work demonstration for the project. Thank you.
Thank you, Mukesh. Before we take questions, I would like to demonstrate our deployed application. Now I'm going to share my screen of our deployed application. This is our code. Can you see this, Professor? This is our code. We trained the data set and tested the data set. I have already run the application. Here, if you can see our application, then you have to log in. Here you can see our Streamlit web application. The main interface provides a text input area where user can paste any text, like even AI or any text. So on the left side bar, we displayed our model performance metrics for transparency, so that way users can know how accurate our model is. So here the accuracy we achieved 98.64%, and the F1 score 98.23%. If you look down here, we already mentioned the specifications, and here are the main model specifications: architecture, parameters, how many samples we are trained, and total details we have displayed here, so that way user can know clearly. Here, to save the time, I would like to copy paste that text from my notepad. This is the article which is generated by AI. I would like to paste this in the input here, so that now we have to classify the text. Here, the background in the behind this input text, it will pre-process the text and tokenized the text and passed to the Distilbert model to predict the result. If you see here, you can see the classification result. This is the AI text which is generated by ChatGPT. So our model shows how much confidence a text is. So here you can see AI generated text. Here confidence is 99.7%. And also to know the user clearly, because they don't know about the technical thing, so we have to show clearly to the user. That's why we showed this confident analysis too. Here if you see the metrics, here you can see the probability of human 0.03%, and the which is the text AI generated 99.97%. Here you can see the recent classifications too. In the left side, you can also see the login, user login, and total classifications 13. And now I'm going to paste another text which is written by me. Now we can paste here and classify the text. So this text is written by me. It's like it's showing human text, a human written text confidence 99.75%. If you see this graph here, confident analysis, it shows clearly 99.8%. The probability of human and AI. Now you can see here AI is only 0.25%. And I'm going to test another data here. This is about the social media, which is generated by ChatGPT. I'm going to test this too. If you classify it, you can see, yeah, this is generated by the AI ChatGPT. So you can see clearly 99.85%, 99.98%. Only 0.02% is the human written. You can see all the data which is now tested. You can see the down recent classifications. And there is the same article which is written by me. I'm going to paste this too to show the difference of AI text and human text. Let me do it big. To paste it here and classify it. See here, you can see the result. This is written by me. Yeah, it clearly shows how much human written, how much is AI written. The confidence is 99.75%. If you see here, the probability of human and AI 99.75% and AI is 0.25%. This is all about our UI interface which we built to classify human text and AI text. AI text. Thank you, Professor. If you have any questions, we would like to answer.
Yeah, so do you know how your model calculate the confidence here?
Professor, based on the statistical and linguistic all these features, it will calculate the confidence.
Okay, so is there any limitation for the input like a text? Like for example, the maximum, is there any maximum
Limit?
number of the words?
Yeah,
Yeah.
so it's like it needs at least 50 words, like 10 minimum characters. So because under 50 words, it won't be able to differentiate exactly, because it would be almost the same for AI and humans. So our system needs at least 50 words for the classification. That's the limitation.
Oh, okay.
And there is the
Okay.
minimum limit for this text. Minimum 10 characters needed to classify it, Professor. If you do less than 10 characters, it's little hard to find whether it is
Okay.
AI text or it will give the input, it will give the result, but it is not extremely accurate.
Okay, so is there any like a maximum number of the limitation for
Can you repeat
500
the
words?
question, Professor?
Yeah, the question is like, so you set up the minimum number of the words, right? So is there any maximum number of the word?
So far, we have worked with the minimum words it needed. For the future scope, we also need to work for the maximum words it can take, Professor.
Yeah.
Okay, okay,
It
great.
depends on the data set, the
Uh-huh.
data.
Okay. Okay, great. Yeah, so let's move to the next team. So the team number 4. So the title is Battery State of Charge Prediction.
Yes, Professor. So
Yeah, yeah, you can
I will
start
be
if you are
sharing.
ready. Okay.
Yeah, sure. Just a second.
Mhm.
Can you able to see my screen, Professor?
Yeah, sure. I can see your screen, so you can switch to full screen.
Yeah, sure. Just a second. So now,
Yeah.
awesome. So when it comes to the project and all, so our project is about AI powered state of charge estimation for lithium ion batteries. So with my teams, Saad Khan and Sudharani Bhavana, and I'm Rohan Amarabi. So just a second. Just so while coming to the problem, we would like to discuss about what actually the problem is about. So I'll just give you an example. Well, we have been moving directly to nowadays. We have been moving directly to the EV cars and all, and even there is a more importance of a battery. Even from the EV to the laptop, we will be using some batteries to be working on. Well, nowadays, based on the temperature and all, they will the estimation of the battery. Whenever we feel like the battery is going to be in a dead position, um, it will, if at all, it will be working on an even in the last stage or so, it will be showing some accurate percentage and all, but it won't be giving that kind of a performance. So at that point of time, we can't even measure properly, like how will you say, while coming to a phone, it says 20 percentage of 20% of a remaining battery, but it will be dying in 5 minutes. I mean, within the 5 minutes, it will be finishing its battery. And I will even in the electric vehicle, it will be giving us telling us about 50 kilometers of a range and all, but it will show us it will be it will be stopping us in the middle of the way. So to overcome this problem, we can actually estimate estimate the charge and also uh, prevent this kind of a problem. So for that, even in like what do we say? For this kind of problem, this is actually it looks very simple, but actually this is a very serious problem. And well, coming to the traditional methods, which just adds up a current in and out buildup or errors over time. Voltage-based methods. I mean, when it comes to the problem states, voltage-based methods are inaccurate because voltage drops when the battery is under load and all. So that's why we are using some smarter methods like AI, when it can look all these factors together, give some better estimation. Motivation is simple. If we improve some SOC state of charge. So what are all the pending voltage pending battery in the pending current in the battery and all. So we can improve prediction battery life, and also we can improve the users' trust in EV vehicles. So while coming to the objectives, so the first thing, I mean, to understand you is the battery behavior. We studied how current and voltage and temperature together affect the state of a battery. And while coming to the second stage, we have tried to build try to build some models to get a better accuracy. So while coming to the model that we have used were random forest and SVR and LSTM algorithm were the three algorithms which we have choose, when even all the three algorithms has given us a tremendous accuracy. When coming to the third point, we have already also tried to show all the metrics which you have been asking for, like RMSE, MAE, and MAP. So, and while coming to the fourth point, we have created a user-friendly application. Where in the end, it is not a web application, but it's a Windows application, where when someone can upload their battery data and predict their SOC predictions instantly. So, instantly, and so the study of a problem builds model and compare them and ship a working tool. So till here, this is all the work we have done, and from the next stage, my friend, my teammate Sudharani will be explaining about the agenda and what all the work is done.
Thank you, Rohan. We'll start with the data sources we used, where we got our data and what it looks like. Then we'll look at some interesting patterns we found during data exploration. This is where we really understood what the battery is doing. After that, we'll explain how we clean the data, build the models, and what the results look like. And finally, we'll wrap up with the conclusions, future work, and live demo of our system. So we'll basically go from what is data all the way to here is the working product. So next slide, please. So in the data sources and description, we have used two data sets. The first one is CSV file containing real battery measurements with 3 columns, that is current, voltage, and temperature, measured every 1 second. So 1 Hertz sampling means 1 reading per second. A typical file has anywhere between 10,000 to 100,000 rows, which means we have several hours of battery data to work with. So the second data set is smaller but very important. It's called OCV versus SOC curve. OCV means open circuit voltage, which is the voltage when no current is flowing. The curve is provided by the battery manufacturer, and it tells us if the battery voltage at rest is the value, then the actual state of charge is the percentage. Think of it like a reference chart. We use the curve as our ground truth to figure out the actual SOC from the voltage readings. So to summarize, we have 3 points. There is current, voltage, and temperature. And from the OCV curve, we derive the target output SOC. That's the basic structure. And next slide, please. Data exploration and visualization. Before building any model, we spend a lot of time just looking at the data, because if you don't understand your data, your model won't either. Here are the key things we observed. First one is the current and voltage move opposite to each other. So when the battery is discharging, current is higher but voltage drops. When charging, current flows the other way and voltage goes up. This makes sense physically. So the number 2 is temperature changes very slowly. It doesn't jump around. But even small temperature changes affects the voltage. There is SOC relationship. So we can't ignore it. Let me give you a typical ranges we saw. Current, so from minus 208 to plus 208, that is charging to discharging. This is EV scale data, not tiny phone batteries. Voltage is from 3 volts to 3 volts when empty to 4.2 volts when it is full. And the temperature is from 0 to 45 degrees centigrade, which is a normal operating range. Now for the target is SOC. We found something interesting when the battery is at rest, meaning no current is flowing. So voltage almost directly tells you the SOC. But when the battery is used, voltage drops due to internal resistance, and this relationship breaks down. This is exactly why we need machine learning. To learn this complex relationship under load conditions, we also checked correlations. Voltage has the strongest correlation with SOC. Current has weaker direct correlation, but it's super important for capturing dynamics, like how fast the battery is being drained. These are the observation guided everything we did. Next, my friend Bhavana will explain.
Thank you, Sudha. Here I'm gonna explain the data preparation. First, we clean and prepare the data before giving to the models. In this, the main issue was the voltage we measure is not perfectly accurate because the internal resistance inside the battery is so when current flow, the voltage drops a little. So to fix this, we adjust the voltage using a formula that adds the back to the voltage loss. This was caused by the internal resistance. And also this gives us a more realistic value called the estimated OCV. Next, here we use this corrected voltage to calculate the battery actual state of charge using a known relationship between the OCV and SOC. Here we also made the sure the values stay between the 0 and 1, they remain valid. After all this, we scale the features like voltage, current, and temperature because they have different units. Without scaling, the model might think one feature is more important just because of the large numbers. Here we can see the LSTM. We add something a bit different. Instead of looking at just one moment, we gave a model of short history here. This helps to understand how battery behavior changes the over time. Also, when splitting the data into a training and testing, we did not shuffle it. And finally, we are missing a values and we handle them using the median values to keep the data stable. Next slide, please. Yeah. In this slide, we can see the modeling and methodology. Now, coming to these three different approaches to compare the performance. First, in SVR, it's a simple model that works well, smaller data sets and gives us a strong baseline. And the second one, random forest. Here we can see that group of decision trees working together. It's a good to handling the complex patterns and also tell us which features are more important in this. And third one, we go to the LSTM. Here, this is the most advanced one. This was designed for the time-based data and the since battery depends on the past usage. LSTM can remember the previous states and make you the predictions. And basically, SVR is simple and also random forest is robust. And here LSTM is the best of time-dependent patterns. Here we can see the evaluations and use the three matrices, right? MAE, which gives the average error, RMSE, which gives more weight to the big errors, and MAPE, which shows the errors in percentages. Using all three gives a complete picture of the performance over there. And next slide. Yeah. In this, we can see the most interesting part was SVR, which gave the decent performance with around 2 to 3% error, which is a good baseline. In the random forest, we improved the results slightly because it was handled to the non-linear pattern better. But here LSTM clearly performed the best, which is reduced the error significantly, almost 40% better than the SVR. And the reason for this is like it just look at the current value, that look at the past behavior using the step 5 window. The extra context makes a big difference in this. So overall, thing is we can say that the battery for prediction models that understand the time patterns like LSTM perform much better than the traditional method. Next, my teammate Saad will be continuing.
Hi, Professor, can you hear me?
Yeah, I can hear you.
All right. So let me just start from here. So the conclusion and future work. So what we have achieved in this project, we built a complete state-of-charge estimation system from scratch. We took raw battery data, cleaned it, engineered features, trained 3 different AI models, and compared them fairly using proper metrics. We proved that machine learning, especially long short-term memory, can estimate state of charge with less than 2% error. That's practical accuracy, not just theoretical. More importantly, we didn't stop here. We built a working application where someone can upload their data and get predictions instantly. That's a real-world value. For the electrical vehicle industry, our work shows that even with simple sensor, uh, just current, voltage, and temperature, we can get very accurate state of charge predictions using AI. No expensive sensors needed. Can you go to the next slide? All right, so our future work. Of course, we are not done yet. There is always more to do. One of them, like the feature we can add in the future, is to add a battery aging into our model. Right now, we assume the battery is in fixed condition, but batteries degrade over time. If we conclude state of health along with state of charge predictions stay accurate throughout the battery's lifetime. Uh, Test on more batteries. I mean, we just focus on lithium, but there are different type of batteries, so we can test our system on other batteries as well. Uh, in the real-time deployment, right now we process data in batches. The next step is to run the inside an actual battery management system. Prediction state of charge every second. This means making our model lightweight enough to run on embedded hardware. Can you go to the next slide? All right, so here is the demo screenshot. Let me just quickly go through the working demo. So this is our interface, which my team mate gonna show you after this. But the first step is the user upload their battery SCV file, the one with current, voltage, and temperature columns. They just drag and drop it to our system. They choose what model they want. I mean, we are trained our system with 3 models, so they have the 3 model options they can choose. Uh, then once they click predict, our system process the data in the background. It does all the pre-processing. The output shows the predicted state of charge is the time series graph, the actual state of charge if available, and all 3 evaluation matrices. The whole thing runs in the browser, just take few seconds and requires zero technical knowledge. That was our goal. I mean, to make AI accessible to battery engineers who may not have machine learning expertise. Thank you.
So I will be taking you to the course, Professor. So, well, I'll be showing you what all the algorithms that we have been using. First thing, we have used random forest and we have extracted the data from it. And the only 3 parameters which are most important for this to train was these 3 parameters. One is current, voltage, and the temperature. So based on the temperature, mostly the performance will be very low. So, well, we have tried it and we have tried to get the better accuracy for that. Even all these metrics have been shown, and there are also another, I mean, different algorithms have been done in the same way. Just the algorithms have been changed, and even few more hyperparameter techniques have been also included just to get more accuracy. So here there's another algorithm being used for this. We have used 10 approaches and the accuracy with all the metrics and all, we have achieved at least 96% of accuracy, based on the random forest. LSTM has given a best accuracy, but sometimes random forest is also giving more better performance than, I mean, achieving more better performance than this LSTM for us when we have been testing it. And the other one, even for this also, we have used the same techniques to work. And here are the metrics and all. So let's go to the UI. So we haven't done much more heavy UI in this. We've directly taken a Windows application. Well, we will be uploading a data set, and we have been trying to upload it and run all the models at a time, and check based on the requirement and all. So here the whole data set information is being given over here, and we can run the models. Just take a small, just a few seconds of a time. So for each and every algorithm, you can just check over here. Which algorithms gives you your best accuracy and everything, and all the algorithm based on each and every data and rows, by reading each and every rows, it will also show the metrics over here and also the best algorithm, which has been predicted well. That will be finalized here itself, as you can see here. It is still running. I think it's still running. So as you can see, yeah, as I've said, you just sometimes random forests has been performing well, and you can see the predictions over here. I mean, based on the actual one and the SVR, just because we have got the huge accuracy, I mean, almost in the same accuracy. I mean, it has been following the same pattern again. I mean, based on the actual one itself. That's why, just because we have got the huge accuracy, even for this also, and mostly all the three algorithms has given us a more than 92% of accuracy. That's why we can only see small, tiny changes in the actual prediction, I mean, actual and around predicted values. So this is how it has been predicted, and here you can see all the metrics and all. This is how the model has been working. And any other questions?
Yeah, so I just have to one comment. So in regression task, so there is no accuracy. So they won't use the concept
Yeah.
of the accuracy. Yeah, so I think you should
Well,
like remove this accuracy part. Yeah, because the accuracy only refers to the classification task. But for the
yes.
regression task, you don't have that. So I just think you need to like just remove those concepts in your final report. Yeah, other than
Yeah,
that,
sure.
yeah, all should be good.
Sure,
Okay. They
Professor.
only measure like how accurate this model it is by like MAE, RMSE, something like this. Okay. Yeah,
Yes, Professor.
so yeah, let's take a 10 minutes break. So let's come back on like um three yeah, let's come back like 10 minutes later. That's
Sure.
3:05 p.m. Okay. So I will close the camera and the mic, just take a 10 minutes break. Okay, and then we can go back. Okay, so let's come back. So the next will be the team number 5. Team number 5 is working on the name entity recognition. So this is also a NLP related project. So team 5, if you are here, so you can just unmute yourself and share your screen.
Hello everyone, good afternoon.
Yeah, you can share your screen.
Yes, one moment, Professor.
Or we can just
Oh, one moment, Professor. Yeah.
okay.
Good afternoon, everyone. My name is Sai Venkata Manoj Maddi, and this is my teammate Vishnu Madpatla. We are presenting as Team 5. Today, we will be presenting our project title Named Entity Recognition. Named Entity Recognition or NER is an important task in natural processing that identifies the classifications and miscellaneous categories from the text. Text data. It plays a key role in applications like chatbots, search engines, and information systems. In two approaches, a traditional machine learning model called CRF, which is conditional random field, and a modern deep learning model called BRT. Using CRISP-DM methodology, we analyze, build, and evaluate these models to understand which approach performs efficiency. Now further,
So hi, this is Vishnu from this side. Here we the named entity recognition is also known as NER is an hello professor, am I audible right now?
Yeah, please go ahead.
Hello,
I can hear
professor.
you. Yeah.
Yeah. Yeah. Firstly, the named entity recognition is also known as NER, is an important task in the natural language processing, is NLP. So it focuses on identifying and classifying entities such as peoples, organization, locations, and other categories from unstructured text. For example, if in a sentence like Elon Musk founded the SpaceX in United States, the NER will identify that Elon Musk is an person, SpaceX is an organization, and United States is an location. So, um, so it helps the converting the raw text into the structured information. So NER is widely used in applications like chatbots and search engines, recommendation systems, and information extraction tools. In this project, we compare the traditional future-based model and a modern deep learning model to understand their performance differences. So the problem statement, the, the main problem we are addressing is extracting meaningful entities from the raw text data. Unstructured text is difficult to process because it does not follow a fixed format. Traditional models often fail because they really on the preferred rules and cannot fully understand context. Example for the word, I'll take the apple. Apple could refer the company and or a fruit depending on the sentence. Modern models improve. Modern model improve accuracy by understanding the context, but they required high computational resources and more complex to implement. So our goal is to compare both approaches and determine which performs better in terms of accuracy, scalability, and real world usability. So the objectives of our project are clear and structured. First, to build a CRF based NER model using handcrafted features such as capitalization and word patterns. Second, to implement a BRET based NER model so that use the contextual embedding to understand the meaning of the words in a sentence. Third, to compare both models using evaluation metrics like precision, recall, and F1 scores. And finally, to analyze the strengths and the limitations of each model to understand where they perform the best. And the CRISP DM methodology. So we followed the CRISP DM methodology to structure our project. CRISP stands for Cross Industry Stand Processing for Data Mining. It consists of 6 stages. So business understanding, data preparation, and modeling, and evaluation, and deployment. So this framework helps in organizing the workflow step by step. It also ensures that the technical work is aligned with the real world problems and business goals. Using this approach made our project more systematic and easier to manage. So here the business understanding. In this phase, our goal was to understand the real work importance of the problem. We focused on automating entity extraction from the large volumes of the text data. This is useful in many industries. For example, in healthcare, it helps like extracting patient information from medical records. In finance, it helps for processing documents and reports, and in customer service, it helps like analyze the chat data. Sorry. Our main objective was to improve accuracy while reducing the manual effort. So we also wanted to build a system that is scalable and can be integrated into real-world applications like APIs. So in slide 7, so data understanding, for this project, we use a CO Conal 2003 dataset, so which is a standard dataset for the named entity recognition tasks. It consider annotations, news articles mainly from reuters. So the dataset include 4 main type entities: person, organization, location, and miscellaneous. It follows BIO tagged format. B means the beginning of an entity, I means inside an entity, and O means the outside of entity. So one major challenge we observed was the class imbalance, since most tokens belongs to the O category, means that there are not part of any entity. This imbalance makes the task more challenging for the models. In the data preparation, in the data preparation stage, we perform the several pre-processing steps to make the data suitable for the modeling. First, we structured the data set properly and ensured that the tokens and labels were aligned correctly. For the CRF model, we created handcrafted features like capitalization, work suffix, I'm sorry, work suffix, and digit indicators. These features help the model identity patterns in the text. For the BRT model, we use the word piece tokenization, which breaks words into smaller subwords. This helps in handling unknown or rare words. We also carefully aligned labels with these sub words to maintain accuracy. This is very important because proper pre-processing directly improves model performance. The
Yeah,
exploded
I
data.
have a question. Is like the PowerPoint slide is done by you or your teammates?
Yeah,
Could
we
you go
both.
back? Could you go back to the previous slides? Why it have like a run up, run down, and non-ramp states? So I believe this is should be like a my demo work, like a seasonal data set, right? So I don't know like why those irrelevant stuff is appear in your presentation slide. Have you do something with the run up, run down, or non-run here? And could you also go the previous slide?
Yeah.
Yeah, the wind farm forecasting. So why you haven't add this one here? Data understanding. Are you like working on wind farm forecasting?
Can you repeat the question? I can't understand. I'm sorry, I am facing some network issue.
Yeah, my question is like, have you done anything with the wind farm generation forecasting? And why the wind farm forecasting is here? The data understanding slide. So that is why I'm asking if this slide is made by you. Or have you like
Yes.
carefully check what's the content appear in your slides?
Yeah, Professor. The slides are made by us.
Then why you add this part?
Hello, Professor.
Yeah.
Yeah, in data understanding phase, wind farm forecasting refers to analyzing usually the meteorological data like wind speed, direction, and power output. This helps in understanding patterns and preparing the data for accurate prediction models. So these are the reason that we put to in the data understanding slide.
Okay, so
I mean,
yeah,
just in short, I can say wind farm forecasting. I mean, why we put here is predicting power generation using wind and weather data.
but is that necessary to do this one in your topic? So you select the NLP one, right? So this is just the entity recognition. What's the relationship between the entity recognition between the wind farm forecasting here?
Okay.
Yeah,
Well,
because
it's
previously
not
in
necessary. Yeah, I can understand it is not necessary. It is completely different from this domain, but including it in our data understanding slide looks irrelevant. But
yeah, in my idea is like I give you like the previous the presentation demo video for you, and you kind of like haven't double check here. You I just ask the ChatGPT to just make the PowerPoint slide for you, and that is why like the AI just have no idea why you want to have this wind farm forecasting. So it's kind of like a made you a combined presentation slide for you, and you yeah, I think the previously I just mentioned, yeah, you are okay to use the AI, but the thing is like you are the one to responsible the outcome of the AI, right? So if the AI just generate like the mixed contents, you should remove them. Okay.
but here, Professor, it's not part of our NRE model directly, but we use it only as an example to demonstrate the data understanding step in CRISP DM is a common
Okay.
across domains.
Okay. Yeah. So
Our focus remains NER, but we kept example to highlight general applicability of framework. However, for more focused presentation, it can be removed.
okay. Okay. Yeah. Please go on.
Yeah, Professor.
Okay. Yeah, I think previously you just go to the next slide or the slide be
Yeah, next.
later. Okay.
So during the exploratory data analysis, we examine the patterns and distributions are in the data set. So we found the most tokens belong to O, and the category confirms the class imbalance, and the sentences lengths are mostly between the 10 to 30 tokens, the which is magnable for both models. We also analyzed the distribution of entity types using graphs. This helps us to understand which entities are more frequent and which are less common. These insights guided our modeling decisions, especially in choosing evaluation and metrics and handling imbalance. From next slide, my friend, my teammate Manoj will continue.
Hello, Professor. On this slide, we can explain our modeling strategy. A model is basically simplified representation of real-world system that help us to make a predictions. In our project, we explored two different modeling approaches, as I mentioned earlier. Named entity for this named entity recognition. The first approach is statistical baseline, which is CRF model. CRF depends on manual engineered features such as word shapes, suffixes, and capitalization patterns. The second approach that we go through is advanced artificial intelligence model, which is BRT. I mean BERT uses contextual understanding and learns deeper language patterns from the text. So our strategy was to compare lightweight traditional model with a more advanced contextual model, see which one performs better on CONNL 2003 dataset. On slide 11, this represents the architecture comparison between CRF and BRT. Here, the base model CRF uses manually engineered local statistical features such as suffixes and case patterns. Its context window is very limited, usually considering only nearby tokens. It optimized using LBFGS, which makes it fast and CPU friendly. On the other hand, BRT is based on 12-layer bidirectional transformer. It can understand the meaning of a word by looking at full sentence context at the same time. So this gives a much stronger contextual understanding compared to CRF. I can say CRF is faster and simpler, while BRT is more powerful and intelligent in understanding of a particular language. Now go to slide 12, evaluation metrics. For evaluation, we use three important metrics: precision, recall, and F1 score. Here, precision measures how many of the predicted entities were actually correct, and recall measures how many of actual entities the model was able to identify, and F1 score is the balance between precision and recall, and it gives us overall measure of model performance. Since the dataset is imbalanced with many non-entity tokens, we used the weighted average F1 score for comparison. This helps provide a fair evaluation of both models. Now go to slide CRF results. The CRF model achieved an overall F1 score of 0.81. It performed reasonably well on categories like location and person, but it struggled more with organization and miscellaneous entities. The main reason is that CRF has limited contextual understanding. It relies mostly on surface level patterns and handcrafted features. So it may miss deeper meanings in text. Overall, CRF gave solid baseline performance, but it had a clear limitations when compared with more advanced models. Now go to results for BRT. BRT achieved a much higher overall F1 score of 0.93, which is significant improvement over CRF. It showed strong performance across all entity categories, especially in person organization recognition. The reason for this improvement in BRT's ability to capture full sentence context. It understands words based on surrounding words, which help it more accurate predictions. So these results clearly show that BERT generalizes better and provides much stronger performance for name identity recognition. Now go to slide 15, which is for comparison of CRF and BRT. BERT outperformed CRF by about 12% in F1 score. This tells us contextual deep learning models are much more effective for named entity recognition tasks than traditional feature-based methods. However, CRF still have some advantages. It is faster, lightweight, and less computational expensive, but this makes it useful for low resource environment. On the other hand, BRT offers better contextual understanding and higher accuracy, but it requires more computational and training resources. So the choice between CRF and BRT depends on application. If the speed and simplicity are important, CRF may be suitable. If accuracy is the priority, then BRT is still better choice. And the challenges and solutions that we came up in this project is the first challenge that was CRF lacked contextual understanding, which is reduced its accuracy. Overcome this, to overcome this, we used BRT, which is understand context better, much better than CRF. The second challenge is training stability issues in BRT. We solved this applying significant gradient clipping, which helped stabilize the training process. The third challenge was BRT acquires high computational power. To manage this, we used mixed precision training, which improved efficiency. Finally, the data set had class imbalance since most tokens belonged to O class. We addressed this by using proper evaluation metrics, especially weighted F1 score, to ensure fair model assessment. Now go to slide conclusion and future work. To conclude, our study showed that BRT is best choice for high accuracy name identity recognition task. It consists outperformed CRF because of its strong contextual understanding. At the same time, CRF is still useful in low resource environments where speed and simplicity matters more than maximum accuracy. For future work, we can explore hybrid models like BILSTM CRF, which maybe combine the strengths of traditional and deep learning methods. We can also work on models optimization techniques like quantization to reduce computational cost. In addition, future improvements can focus on real world deployment so these models can integrate it into practical applications such as chatbots, document processing, and intelligent search tools. Now, final slide. Thank you. We hope comparison between CRF and BRT gave clear understanding of how different NER approaches perform under CRISP DM framework. Now we would like to happy to answer the questions. And before showing the code, I just want to give you a note here, Professor, that BRT model requires significant computational resources and time for loading and inference, especially without GPU support. Due to time constraints, this demo environment, the execution is taking longer than expected. However, we already successfully run the full pipeline earlier and obtained the results.
Okay, great. So yeah, no question. Yeah, so let's move to the last thing. Yeah, so last thing's title is floating object detection using drones. Okay, so
Hello, Dr. Leo. Just one moment. I'm getting my presentation up and ready.
Okay, okay. Yeah, so just a quick update for team number 6. So currently the drone battery, like Dr. Hao told me, well, the battery previously it's kind of like a missing a compatible adjustment cable. But right now we have the cable, but it still doesn't fit. So I don't know. Yeah, maybe we will need to ask the Valkyrie. They want to just having something to yeah, maybe we need to purchase another one and still need to wait or something.
Yes,
so
Dr. Leo, I understand. I understand the situation.
Yeah.
I mean, I think that could be included as the future work as well.
Yeah.
Because hardware components are always questionable and not controllable.
Okay. Yeah, previously I also see the Maddie, right? Maddie raise the hand. So is there anything you want to say or just mistakenly press the button to raise the hand?
Yes, Professor, I just want to show the code for my team project NER. So that's the reason I just want to raise the hand.
Oh, please go on.
Okay. Yeah.
I can stop sharing the screen. Please go on.
Okay.
Thank you, Harsha. Thank you very much. Here, Professor, the code is still running from past 1 hour because the BRTs takes high computational time and accuracy too. So it is taking more time to show me the results here. Here in import section, we imported all the required libraries, pandas, nummify, and are used for handling data and Matplotlib and Seaborn are used for analysis and visualization. And sklearn and CRF suite is used for the CRF model, and transformers with PyTorch are used for the BRT model. Here you can clearly see the things that I'm importing into my code. And here in the project overview, here we define the task which is named entity recognition. The data set is CONNL 2003, as I mentioned in my presentation. And the target entities are person, organization, location, and miscellaneous. Now go to dataset loading. This section loads the data set into a train, validation, and test sets. The dataset already contains tokens and their entity labels, so we use it as the main source for training and evaluation. Now go to labeling part. Here, label mapping, we define the bio tagging format. B means the beginning of an entity, and I means inside the entity, and O means outside an entity. This is the standard labeling format for NRE task. So we used that approach here. And data conversion. This part converts the data set into a structured data frame format. Each row represents a token along with its sentence ID and label. This makes pre-processing and future extraction much easier. Let's move on to pre-processing. In this section, we clean the tokens and generate useful features such as whether the token is alphabetic, numeric, uppercase, and its length. These are the important handcrafted features, especially for CRF model. And you can clearly see the table that we use it for training here. And now go to label distribution. And this part is used to understand the data set better. We analyze the label distribution, entity distribution, and sentence characteristics. This helps identify issues like class imbalance because most tokens belong to the O class. Now go to CRF future engineering. Here, here let's see that how tokenization works here. This section prepares the text for BRT. Since BRT works with the subword tokenization, that sentence is split into BRT compatible tokens before training. Now go to label alignment. Because one word can be split into multiple subwords by BRT, this function aligns the original entity labels with tokenized representation. This is necessary for correct training and prediction. Now go to BRT model. Here we load and pre-trained BRT model for token classification. Then we fine tune it for named entity recognition by setting the output labels according to the entity classes. Now we can see here training phase is also there. In this part, both models are trained. The CRF learns from manually engineered token features, while BRT learns contextual language patterns from the dataset. Here in this section, generates predicted entity labels from both models. For BRT, the prediction logic also handles subword tokens and maps the results back to the original words. Here and in this evaluation, we evaluate both models using precision, recall, and F1 score, as I mentioned in my presentation. F1 score is most important metric here because it balances precision and recalls. And here you can check the comparison here. This section compares the final performance of CRF and BRT. The key idea is that CRF is simpler and faster, and while BRT provides a better contextual understanding with usually higher accuracy. So overall, this code shows the full workflow: the data loading, pre-processing, feature extraction, CRF modeling, BRT modeling, prediction, and final evaluation. As I mentioned earlier, Professor, BRT is computationally heavy because it is transformer based model with many parameters. So execution is slower on CPU compared to CRF. Thank you, Professor.
Okay. Yeah, you can show the result like later, like via email when you have the running result. Okay. So next we
Definitely,
can
Professor.
yeah, next we can move to the team number 6.
Yes, Professor. Good afternoon, everyone. I hope everybody is able to view my presentation and is able to hear my voice clearly. My name is Harshvardhan Verma. My project is floating object detection using drones. The short form is FOD. I could work a better naming convention in the future, but so the abstract or the project motivation is that for the purposes of surveillance, emergency services such as search and rescue, disaster management, and many other aerial related activities, using drones or UAVs for the use cases specified above is considered best because they have huge potential as they have the best aerial flexibility. Now, FOD CV, floating object detections using drones and computer vision, is a drone that specializes in the detection of floating objects in water environments like lakes, rivers, and seas. By using computer vision, we can perceive, detect, and classify what the floating object is from a higher aerial view. This project is aimed to introduce a quick response system that integrates surveillance and potentially environmental research as well. So for us to achieve this, we need a data set that comprises of images that are in the best interest for this particular project. So the data set that I got was from Dr. Liu, which is an aerial floating object data set from Kaggle. So with having a scarcity of labeling data based on the use case, we also looked for an alternative solution, which will be revealed in the later slides. So the project objectives were to conduct an intensive research on the current state-of-the-art technologies and models that deal with object detection and aerial environments, to train and test the metrics of the models which have been identified by training them to convergence, observing and analyzing how well different models perform from the same data set, exploring the solutions for limited labeled data, deploying the ideal model which can be run on an onboard CPU like Raspberry Pi. The data set used in this project is from Kaggle, like mentioned earlier. The link for the data set is available here. So the AI4 dataset is the first free dataset for training machine learning and deep learning models for maritime research and rescue operations. It contains aerial drone videos with 40,000 annotated persons and objects floating in the water, many of small size, which makes them difficult to detect. The AI4 dataset contains images taken from 50 video clips containing objects floating on the water surface captured. All of this is a description about the dataset. It contains 3,647 images, which have been split into test, train, and valid. As you can see, the ratios are given below. These are two sample images from the images. These are two sample images from the dataset provided. So all of these are labeled by the providers. So I chose YOLO in order to move forward with object detection, and the 5 models um, which are the latest and currently leading um, for the use case of aerial vision are YOLO V8N, which is a nano model of the YOLO V8, YOLO V8L, YOLO V10N, which is nano version, YOLO V10L, the large version, YOLO V10. That is my mistake for including an N. So YOLO follows the same similar data preprocessing steps across all of its models. So so the data preprocessing steps followed by YOLO in order for it to convert the raw data set images into a format where the neural network of the YOLO could understand and process it is given below in these following steps. The first step is the aspect ratio preserving and resizing. The second step is letterbox padding. The third step is mosaic augmentation. And the fourth step is tensor conversion and normalization. Professor, I have slides explaining each of the data preprocessing steps in detail. Should I go through all of those slides in detail, or would you like me to brief it up?
Yeah, you can briefly talk about that.
Got it. So what aspect? So the first step starts with aspect ratio preserving and resizing, which is scaling the image. So what happens in this image is that so initially the data set comprises of images that go from 1920 to 1080 pixels all the way up to 3060 and 1080 pixels. So what this step does is that it takes in images and it scales them and shrinks them down into a 640 pixels image while still retaining the original features of the image. So a well-scaled smaller image is produced which retains its true proportions without losing any quality of the image, which means the objects included in the image, like the humans, boats, and etc., would also not lose their features. The second step is the letterboxing, which is the padding. So this step takes the scaled image from the previous step, which is still rectangular, as an input. Oh, I apologize. Yes. So the neural network that will be used still requires a 640 image input, and to fill the missing space and make it a perfect square, YOLO pipeline adds solid borders to the short sides of the image, which will make it into a square. These borders are gray in color, and the output would be a 640 times 640 square. And how this would look, there's an image at the end of the explanation, which will make more sense. The third step is the mosaic augmentation. So after the images have gone through steps A and B, 4 images are selected at random from our training data set. Now these 4 images are strung down and then attached together into a 2 times 2 layout to form a new 640 x 640 square. So the center point of these stitched images are randomly offsetted, and a composite image is outputted. So by shrinking for 4 images to fit into the space to one, the floating objects become much smaller. This forces the neural network to get really good at identifying tiny features. The last step is the tensor conversion and normalization. So the new image from the previous steps is then read as a 3-dimensional array with integer values. Its shape is represented as height, width, and channels. So this 3-dimensional array is represented as height, width, and channels. PyTorch is optimized to process color channels first. So it would be in the order of channels, height, and width. Now let's assume an example of 3, 640, and 640. So these large whole numbers would cause exploding gradient problems when the neural network would process this particular 3D array. So in order to fix this, every pixel value is scaled down by dividing by 255. GPUs are then designated to parallel processing, which takes multiple processed images at once, depending on our batch size, and stacks them together, which adds a 4th dimension. So this is the sample output. As you can see that the images have been scaled down, reattached together. If you can see the first row, 4th column image, it shows you how the center is offsetted. The same can be displayed with the other images as well, on how they are strung down and stitched together in order to form a complete image. So what are the metrics that we have used through YOLO, which are generated by YOLO in order to explain our model's performance? The first metric is precision. So high precision proves that the model is not just hallucinating by just assuming and mistaking sun reflections or wave crests for swimmers. So how the precision has been derived? It has been derived by this particular formula. Recall. High recall guarantees that the model is not blind to tiny objects when it perceives it from a minimum of 10-meter altitude. F1 score, a unified metric proving the model is well balanced and isn't sacrificing precision to artificially boost recall. The MAP50, it proves that the model can successfully locate the general vicinity of a boat or human in the water using a baseline 50% intersection over union. MAP50 295 is the ultimate proof of SAM refinement methodology. A high score here proves the pipeline successfully taught the YOLO model to understand exact pixel boundaries and not just general locations. So as mentioned before, we have used YOLO model in order to achieve this. A little bit about YOLO is that YOLO in its full form is known as You Only Look Once, which is a state-of-an-art real-time object detection system. Unlike traditional AI that scans an image multiple times in order to find objects, YOLO passes the entire image through a single neural network just once. This allows it to simultaneously predict what an object is and exactly where it is located at incredibly high speeds. Now, earlier, uh, I I have spoken about tackling the issue of auto labeling or how to refine our data set better. So this is where segment anything model comes in. Segment anything model has been created and introduced by Meta. It has a broad using SAM model, especially for computer vision, especially in the area of computer vision. It completely transforms how data sets are being generated and made. Because usually, realistically speaking, there is only very limited data available over the internet to train our model uh, uh, to achieve higher precision or to achieve higher accuracy. So what segment anything model does is that it auto labels the images, or if you have um, s- uh, or, or it might take in your existing labeled data set, and then using that data set, it can refine and label objects further, um, and refine your data set. So the foundation model for prompt-tuple image segmentation is the core is given below. So the core architecture, the image encoder, it processes the high resolution image to extract dense feature embeddings, evaluates multi-scale context to distinguish micro objects from vast backgrounds. Prompt encoder translates human inputs into strict mathematical boundaries using learned embeddings. Mask decoder. Mask decoder fuses the image and prompt embeddings via cross-attention to snap a pixel-perfect polygon masked strictly around the target object. The semi-supervised implementation is, rather than blindly auto-generating the labels, human-verified YOLO bounding boxes are fed directly into the predictor module. The decoder isolates the rigid object geometrics from dynamic noisy backgrounds, as in it gives pixel-to-pixel identification of the object uh, rather than when compared to the original labels from the dataset. So these are the metrics that have been displayed when training YOLO models V8N, V8L, V10L, V10S, V10N over the dataset using the original labels. As you can see, the metrics are precision, recall, MAP50, MAP50 to 95, and F1 score. So this particular graph has been generated from an experiment and research conducted on which model would help us achieve higher metrics, considering the onboard CPU limitations in mind. And these are the metrics achieved after using SAM to refine our labels and SAM generated refined labels. So there is a huge increase in the MAP 50 over 95 because it eliminates the possibility um, of background noise, and it just targets the pixel to pixel object. After experimenting on SAM and choosing YOLO V8N, considering for its metrics, F1 score, and its compatibility with the potential onboard CPU, which I'm hoping to be a Raspberry Pi, we have moved ahead and took a step forward and implemented SAM2. SAM2 is the second version or the upgraded version of the initial segment anything model. So the key differences between SAM and SAM2 are SAM2 utilizes an HIERA image encoder, which is an hierarchical image encoder. It processes images at multiple spatial scales simultaneously, extracting high-level global context and low-level micro details at the exact same time. SAM2 features a significantly upgraded mask decoder trained on a massive video dataset, giving it a much sharper mathematical understanding of edges and contrast to slice through visual ambiguity. SAM2 employs aggressive token dropping. As the HIERA encoder processes an image, it mathematically discards irrelevant background data, making the model significantly faster and less demanding on the virtual RAM. Upgrading to SAM2 solved the three most significant bottlenecks encountered while building the floating object detection while building FOD. So solving the micro object challenge. So at a 10-meter altitude, the objects which are in my data set are swimmers and kayaks, which would be tiny clusters of pixels. So SAM flat processing can easily lose these targets in the massive ocean background. Whereas when using SAM2 HIERA encoder, it maintains the macro context of the water while simultaneously zooming in on the micro features of the subjects, beating the splashing water problem. Floating objects generate wakes and swimmers generate splashes. SAM1 frequently included this irrelevant white water inside the bounding box masks. SAM2's upgraded boundary precision acts as a geometric knife, cleanly separating the human from the splash. This mathematically perfect data is what directly drives up the strict YOLO MAP 50 to 95 metric. By eliminating the, it also eliminates the hardware bottlenecks where where processing hundreds of high-resolution aerial images previously exhausted Google Colab computational units because SAM2 drops unnecessary background tokens. The semi-supervised loop processes the dataset much faster and avoids crashing the cloud runtime, allowing for rapid dataset refinement. So these are the metrics achieved after using SAM2 on the dataset and trained on YOLO V8N. As you can see that the F1 score has a huge boost from when it was initially refined using SAM. And the same would be with the MAP 50 to 95. So overall, by using SAM2, our data set has been further refined and the model performs better with this refined data set. An example output of the SAM architecture would be displayed here. Just give me one moment. Yes. So this is the output label box generated using SAM2 dataset. So as you can see here, the bounding boxes have been very closely generated using SAM2. I will show you the original bounding boxes as well. Just give me one moment. Yes. So this is the initial labels that we have gotten from the data set itself. As you can see that there is a lot more of background noise involved in this particular original labels, which would prevent the model to detect the objects accurately with all of the background noise in the bounding box. Our future work would be to integrate the model on board the UAV, which I'm hoping to be a quadcopter or a hexacopter. Work on the aerodynamics of the drone itself. Look for possible power sources for the UAVs in order to have longer flight time. Work towards achieving a completely autonomous flight, further exploring Meta SAM's auto labeling capabilities. This is what I hope to achieve in the future by continuing this particular research project. Now let me show you a quick demonstration of our converged model. So what I did is that I took a sample piece of from our data set and made a video out of it, which would then be used by this script in order to use YOLO VN model on top of it. So this is the final output that I have been able to achieve from my system. Now the future step would be using this on the onboard CPU that would go on the UAV and test how it is performing and then improving its FPS and etc. Thank you.
Okay, great. Yeah, so yeah, no question. Yeah, so yeah, I think all of you made a great job. So next thing is the next week we will submit the first draft of our final report. So I believe I already made a video to talk about this one, and hope you can follow the specific format. Yeah, so after that, so I will just briefly review your report. So if there is any a format issue, then I will need you guys to make changes. And for the draft one, so you guys only need to submit the Microsoft Word version. So just the one team, one submission is fine. But for the finalized report, that is everyone need to submit. And also yeah, and after that,